The W.W. Hay Railroad Engineering Seminar is sponsored by the National University Rail Center here at the University of Illinois Urbana-Champaign. On behalf of all of us, we thank US DOT and our industry partners, CN Railway, BNSF Railway, Hanson Professional Services, and Union Pacific Railroad for their ongoing support. It's greatly appreciated by those of us here on campus, as well as all of those participating via the internet. Speaking of everybody joining us by the internet today, it includes a long list of organizations. I think there's well over 100, 150 people registered for the seminar as of a few hours ago. Various railroads, Class 1 railroads, various suppliers, various competitors, right, are all logged on. We also have some representatives from Transnet in South Africa, so a great international participation for the seminar. Also some of our academic colleagues from KTH over in Sweden are also tuned into the seminar today. So very exciting to have them join us online. So those of you who are connected remotely, if you wish to receive PDH for your participation, please send the RailTech seminar email, an email with your information as described in the email announcement for the seminar. Okay, so today's presentation addresses the future of heavy haul freight operations. As the cost of freight transportation continues to rise, solutions to optimize the movements of trains becomes paramount for the survival of railroads and their associated businesses. Heavy haul freight trains serve a distinct purpose in moving goods, and depending on the goals of the railroad and the businesses they serve, there are many areas for optimization, such as reducing fuel consumption and time to destination, and obtaining greater overall general operating efficiencies. Autonomous train operation provides the opportunity to obtain these efficiencies by controlling, and in some cases eliminating, costs associated with crew changes, operating consistency between train drivers, and train marshaling. Some concepts, such as train platooning, which is the subject of a joint research project we have with New York Airbrake and some of our academic colleagues that's currently underway, sponsored by the Federal Railroad Administration, are ripe for potential solutions to further expand on the effectiveness of automation. This presentation will explore one successful and currently operational implementation of automation by railroad to optimize train operations. So we're excited to have three speakers here today from New York Airbrake, which is a leader, no pun intended, in locomotive driver advisory systems and autonomous training technology. Joining us here on campus today is Chuck Coyle, who's Director of Services for New York Airbrake. Chuck has 30 years in railroad product sales, management, and services, ranging from airbrake overhaul and elastomer manufacturing to high-tech locomotive brake and train control. Chuck's been employed by New York Airbrake for the last 23 years, and he also happens to be a communications graduate of the University of Illinois Urbana-Champaign. So welcome home back to campus, as they say here.
Thank you.
Joining us on the phone, basically due to some inclement weather-related flight cancellations coming out of upstate New York, who had hoped to join us in person, but will be participating in the seminar remotely, are two of Chuck's colleagues from New York Airbrake. So first we have Bill Kleftis, who is Vice President of Engineering with New York Airbrake, with a 35-year history of engineering and operations of various industries, including railroad products and systems. Bill has been employed by New York Airbrake for 7 years with a focus on new product development, including the leader system. Bill has a BS in Chemical Engineering from Rensselaer Polytechnical Institute, and an MBA from Babson College in Massachusetts. Our second remote presenter is Rich Matusiak, who's Director of Systems Development Engineering, and has worked for New York Airbrake for the last 24 years. He's held various positions in organizations, starting as an electronic hardware development engineer, and then moving up through various product development and management positions. He's helped develop numerous electronic, electromechanical, and mechanical products within the New York Airbrake product portfolio, including 13 years on the leader development team. Rich has an Associate's in Engineering Science from Mohawk Valley Community College and a Bachelor's in Science in Electrical Engineering from Syracuse University. So we're very excited to have New York Airbrake here today. So please join me in welcoming Chuck, Bill, and Rich for their seminar entitled Development of Autonomous Heavy Haul Freight Trains.
I'll kick this off very quickly ahead of handing it over to my colleagues. As you can see on the screen here, we've got two buildings shown. The one on your left is our Watertown, New York headquarters. New York Airbrake has been in business in Watertown, New York since 1890. Very few companies can say that they've manufactured in America that long, and still are, which is a tremendous tribute to the people there. Unfortunately, my colleagues aren't there because the snow today is up over the bottoms of those windows. They were beneficiaries of the lake storm that hit yesterday. On the right is our Train Dynamic Systems offices and laboratory in Irving, Texas, which is where the leader system is based, headquartered, and developed. Without any further delay, I'll hand it over to my colleagues to present.
Thanks, Chuck. Pleasure to have this opportunity to present this information, and hope to get some good dialogue going with everyone as we go along. So Chuck, if you'll head to my number 2 slide. What I'm going to focus on today is really one of the implementations that we've had for Leader with a railroad in Western Australia, which is Rio Tinto. They have an iron ore mining operation in Western Australia. They faced a few issues several years ago, as many railroads do, with trying to improve the capacity as well as efficiency of their operation. They began a project back in roughly 2010 to enhance their rail capacity. So what I've got here is some of the highlights of the project overview from Rio Tinto's standpoint. So their plan was to expand their iron ore capacity by automating their mainline locomotive operations from the ports to the mines. This ended up becoming known and is a registered trademark of Rio Tinto as their auto haul operation. That's their name for their overall autonomous train project. And feel free to Google that, as well as look on YouTube for various different videos and overviews. They're very proud of the project, and there's additional information to be found on the web that they've provided. The operational objective was to deliver loaded ore trains from the 11 mine sites to their 7-mile location and Cape Lambert yards to then export via the sea. And then return the empty trains back to those yards in the mines to again get filled up and repeat the operation. So essentially what they were trying to come up with is a method to create a conveyor belt from the mines to the ports that would run efficiently and effectively and minimize the delays and the overall cost of operation. So the overall network that Rio Tinto Iron Ore operates is privately owned. It's the largest privately owned network in the world, and it comprises more than 1,400 kilometers of standard gauge track. The network does not interconnect with any other rail networks and is completely isolated. All right, proceed to the next slide there, Chuck. Okay, so the Rio Tinto rail network operates 24 hours a day, 365 days a year. Existing operations throughout the network currently require at least one, or required, I should have changed that, required at least one locomotive driver for each train. Some of the mine sites, due to their location, require pusher locomotives. They call them bankers in Australia. So that includes an additional driver at the rear of the loaded trains to help provide additional tractive effort to push the trains over the top of the hills. Currently, those banker drivers are still required to ensure the separation between the locomotive and the train occurs. One of the additions that they are still investigating but has not come to fruition is the automation of those bankers, complete automation of those bankers. They do get automated from an operational standpoint, but from a disconnection standpoint, they cannot decouple from the train on their own at this point in time, based on their current operating procedures. Rio Tinto employs a team around 500 mainline and yard locomotive drivers. The mainline drivers operate on 12-hour shifts maximum in accordance with operational safety policies, work procedures, and government legislation. Each locomotive driver has a base location, not unlike what it is in the rest of the world. Operating schedules try to ensure that drivers are returned to their base at the end of each driving shift. Unfortunately, that's not always possible, primarily because of operational disruptions. Where the return to a base is inside 12 hours is not possible, arrangements are made to move the drivers as necessary. This introduces additional delays and also exposes personnel to additional risks that are inherent to transportation by road in the Pilbara, which is not exactly the nicest country in the world to be traveling through. Most injuries and accidents occur in light vehicle incidents, not in mainline train operations. All right, additional projects that were supporting the project are 7 TDS 6000 simulators, which we provided with the assistance of a division that we formerly had in Australia to provide training for the various drivers, as well as capability for additional analysis and understanding of train operations by others within the organization, as well as the many contractors that were involved in developing this autonomous train. Additional variation order that was provided in September of 2012 also resulted in the inclusion of automatic train protection updates. This was to assist with understanding how the automatic train protection system would interact with the trains in the various scenarios. And then eventually the auto haul updates were put into the systems and provided. In addition to the desktop sims, test bench train simulators were provided as analysis stations for the operating and mechanical groups so that they could understand how the system was intended to operate and run tests of how the system was integrated with the rest of the locomotive and train operation. And then initially, another initial project as part of the program was that we provided a standalone leader driver assist implementation in the middle of 2014. And this provided a baseline set of data that we could understand how the trains were being operated, as well as how what the efficiencies were that were going to be gained later in the project, and provided that baseline set of data. On to the next slide. So this obviously wasn't a project that was just taken on by Rio Tinto and or New York Air Brake. There were a number of different companies involved in putting this project together and realizing the actual implementation. So what you'll see is that New York Air Brake had 3 different locations that we had people involved. One in our Irving, Texas office, as well as one in New York Air Brake Sydney office and a Perth office that we established as this project moved on. Additional partners in the program were Ensaldo STS, which is now Hitachi, and WebTech provided some of the other peripheral pieces that were involved in the implementation. All right, are you on slide 6 there, Chuck?
I am.
Okay. So the operations for Rio Tinto. So as we started to deploy what we call leader AutoPilot into their auto haul operation, had to understand what the makeup of the overall railroad was, what the trains they were operating are, what the equipment is that they have. So obviously, as I said previously, there's approximately 1,400 kilometers of track that Rio Tinto has. The target was to automate approximately 1,200 kilometers of that track with leader AutoPilot and the other remaining pieces of the auto haul operation. This was going to be accomplished on 180 GE Evo 44 DC locomotives, as well as 20 GE Evo 4400 AC locomotives. We're currently in the process of deploying on the AC locomotives. The initial implementation was on strictly on the DC locomotives. Their train makeup is 3 head-end locomotives plus 236 cars. This results in a loaded weight of 33,000 tons, where pushers are employed as needed, and the top speed that the train is able to achieve at any point in time is approximately 80 kilometers per hour or 50 miles per hour. The other thing about this train is all the cars that are in the train are ECP equipped. No cars in this use conventional pneumatic braking. It is strictly a pneumatic controlled system. So currently, greater than 97% of the runs that Rio Tinto makes are driverless from port to mine and mine to port, and they're operating over 20,000 kilometers per day using the system. They average approximately 60 trains per day from mine to port, with an average of approximately 400 trains per week across the system. Going to the timeline of the project. So New York Air Brake entered the project with Rio Tinto back in 2011. We were selected. New York Air Brake's leader system was selected specifically to be what's deemed now as the driving strategy engine part of the auto haul system. So this means that the system would be responsible for making choices on how to operate the train from an optimization standpoint, as well as actually implementing the control of the train and the control algorithms. In 2013, we did a model validation. So there was a series of iron ore cars that were instrumented, and a study was done to ensure that we had a good correlation with the models that we were using. In 2014, we began on-track testing and our driver assist operation that we said to get our baseline data. In 2015, attended operations started. So that meant that our auto haul algorithms and AutoPilot algorithms were then started to be used under supervision of various drivers, as well as other senior management people overseeing the project, and began testing on how the system itself is operating, as well as the criteria of how we are actually trying to operate the trains. In 2017, began our first fully autonomous run, where the drivers were on board or management was in oversight, and began stepping away from the trains to understand if the train would maintain autonomous operation with all the various checks that we were doing on board the the train from a safety aspect as well as how the train was being operated. And then in 2018, we went into fully autonomous production, which means that at that point in time, greater than 90% of the trains were actually being successfully operated autonomously. With this, once we went into production, the trains, based on the data from Rio Tinto, they were seeing a 12-year historic low for train brakes, meaning that the system was actually able to take into account the reactions and the understanding of the train movement better than the operators in some cases, and adjust to ensure that the operation of the train was as smooth and that we were managing in-train forces better, I should say. So what were some of the specific functions that we included in with AutoPilot for the auto haul project? Safety function and verification activities became critical. So the driver strategy engine has one safety function, and that is controlling in-train forces to prevent a safety incident. To achieve this, we had several studies that were conducted to prove out the accuracy of the model and the static information that we were using as part of the system. One of these was the iron ore car in-train force study that I previously mentioned. The in-train forces were measured in the field on various iron ore cars distributed throughout the train that fed data back to an overall database, and then we made improvements including different type of draft gear, as well as found some issues with track data that was being provided. So the majority of the changes that were made for the system weren't the actual models themselves, but the data that was feeding the models, the static data that was feeding the models from a car standpoint. So much of that had to be updated as the assumptions that were made going into the project on what was part of the cars. From this analysis, we were able to determine where the areas that we didn't understand the train well enough and get further data from both manufacturers and maintainers of the cars and the track to improve the data set that we were providing into the algorithms. We also verified the locomotive models as part of this, not just the car models. We measured the supplier data against the field data and updated the locomotive models as necessary. And then we also verified the test environment. So the simulations that we're using for the software engineers as well as the operations people to verify the operation that we were trying to develop. The simulations were then verified further and created a test bench for us, both for the customer as well as for us internally, to ensure that any modifications that we were making were still appropriate and successful. So jumping down to the overall system overview of what was included. So the AutoPilot system, again, was part of the overall auto haul system that was being provided. So what you see in the on the right-hand side is the box around the DSE system. That is what we were providing as the driving strategy portion of the system that we were developing. Everything outside the box was being provided by one of the suppliers outside of New York Air Brake, so either Insaldo or Wabtec primarily. The cab display unit we did provide for part of the driver assist trial and baselining, but for long term that was integrated into one of the onboard displays. So on the left-hand side of that box, what's designated as New York Airbrake TDS COTS computer. So that's where the leader core algorithms reside, as well as the driving strategy itself. So understanding what the train makeup, location, and base static info on the required for the models that are used, and then the throttle and brake commands that were being developed, as well as the in-train force information. All this would get fed to both the display in front of the engineer, as well as the control system that was going to control the train from a locomotive controls perspective, and additionally to the rules checker and safety supervisor. So one of the things that we had to develop as part of this to take it from a SIL 0 system with no safety integrity level associated with it to a SIL 2 system was to put some validation around the commands that we were providing to the locomotive control computer. So the rules checker and safety supervisor was developed as a separate code base and by separate developers to take information that the leader core was providing to control the train and verifying it against the information that was being provided directly from the about the track, the position, and so forth from the actual railroad. Through these two, the commands were verified, checked, and ensuring that an unsafe situation wouldn't be created. If so, the train was brought to a safe condition, either a stop or into a notification. There's various different degradation modes that are part of the system, and the rules checker and safety supervisor was responsible for that. I think that's it with respect to that slide. So as I talking a little bit more about the rules checker and safety supervisor. So like I said, it was created to check the output of leader. So our CSS runs its own train model, developed under SIL 2 software standards and development standards. And what it essentially would create is its own model of what the in-train forces would be, and then compare those against what it was thinking the in-train forces being supplied by the leader models would also be. Through that would understand whether or not the two aspects were converging or diverging, depending on how those were being operated, would then make adjustments or provide feedback to the system, or bring the train to a safe state, as I stated earlier. And the important piece of this was that it was trying to make sure that the models are staying in agreement, and if they aren't, make sure that we don't put the train in an unsafe state. So on to the next one, leader prompting and driving strategy. So what are we providing as part of the driving strategy engine? So leader AutoPilot, it does a look-ahead simulation. So essentially what it's doing is going through a number of scenarios to try to simplify this, trying to show this with the diagram shown. Looks through various scenarios of conditions of, applying brake, applying throttle, different notch settings, and trying to simulate in the background and forecast what exactly the train will do as these changes are made. So it does this in a whole series of simulations to ensure that we understand over the next 800 miles what the train is actually going to be doing based on the next set of decisions that we're going to make. We ensure that the prediction horizon is far enough ahead so that we can react to the appropriate braking situation or appropriate throttle change situations, as well as ensuring that we're meeting the optimization demands that the customer has put on us based on what's being supplied as part of the operating plan for this particular run. Any questions up to this point? I've thrown a lot at you so far. Okay, continuing on. So what were we able to achieve at Rio Tinto? So overall, since the beginning of 2019, Rio has successfully been able to run more than 90% of all of the kilometers that they've traveled without a driver on board. The two graphs on the right show the number of kilometers per day, with the bottom right graph showing the cumulative kilometers traveled, and split by the different software releases and the number of locomotives that were actually released for operation. And the emphasis there is that the adoption of autonomous trains at Rio has occurred. Some of the efficiencies achieved to date at Rio Tinto, more than 4.5 million kilometers have been in fully driverless mode safely and successfully. Greater than 97% of the journeys on any day are driverless. Maintenance costs have decreased due to the repeatability of the operations. Failures are more confined and predictable, allowing predictive maintenance. Repeatability driving means that planning is much easier. So they know when they're going to get to the port, they know when they're going to get out of the port, and the flow is much better. 6% speed improvement is the big benefit, and this is really what Rio Tinto was looking for right from the beginning. They wanted to increase the overall velocity of their operation, and by being able to have an autonomous operation from mine to port allowed them to eliminate the crew change points, which was found to be, in previous analyses, found to be one of the biggest contributors to the slow operation of the railroad. This eliminated those, and therefore ended up with a speed improvement that has been achieved. And you can see that the savings in the changeover of the drivers, the crew change points, was at least 1 hour per journey cycle. So what did this all end up in? So Rio Tinto achieved a world's record with the world's heaviest robot. That can be seen in the Guinness Book of Records 2020 on page 155. They're looking to exceed this record with increasing the overall tonnage that they're capable of moving over time, but are pretty well satisfied at just hitting this achievement. So one of the things that I've included here is a link to a video that Rio Tinto put together to demonstrate what they've achieved and the people involved.
Load autonomous train from Tom Price to Cape Lambert, our next step towards full-scale autonomous operation of the railway.
Very excited, can't believe we finally got to this day.
I was told to count the number of people that have been involved in this process. This project's been going on for the better part of a decade in various forms. It touches lots of parts of our business. I would say it'd be in the hundreds.
My role today is to set up a driverless train, check that it's done safely and ready for departure, liaising with train control and then to stand clear and send it on its way.
My process involved with the driverless train today will be talking with the auto haul crew to make sure that the train is presented to train control ready for departure. And once they've confirmed that that's the case, then we'll proceed with our auto haul scenario to make the train take the journey through to the ports.
I'll liaise with train control in Perth and we'll do our tests.
98 with control, we'd like to go update you after.
Roger.
And 81 98 West Control, data's validated and auto haul start doing.
West Control 8198, yeah, you got auto haul, mate. And then I'll exit the cab and train control in Perth. They'll program the train and it'll go to the coast unmanned, and this will be the first event of a heavy haulage loaded train from a mine to a port worldwide.
I think it will change how quickly it happens. We don't have to worry about changeovers. I just think going forward, it's a big business improvement.
I always knew we'd get there, and you know, I'm really proud to be part of the technology, and you know, it's a huge, huge milestone in global rail operations.
It's great to see a train coming. We dreamed it, and now finally we made it. And I think it's really a big recognition of the big effort, all of the team, of united team of Rio Tinto and Southwest STS.
We're making history today.
So what do everybody think about that? While, you know, this is a bit of a unicorn application with standardized equipment and almost perfect conditions of uniformity of cargo, there are so many things we could draw out of this application for advancements in our own North American and other global technologies.
I think you need to close the YouTube channel and just explain the next video.
We're working on it.
Sparse population. Explain why the country finds itself at the forefront.
Well, while they're yes, so what do you guys see as sort of the biggest challenges to adapting this technology to the North American environment?
Well, one of the first things you see here is this was an all ECP train, and you know we made a great effort for ECP 10, 15, 20 years ago here in North America, and by the very nature of our interchange system and our ADR system, which gives us the greatest freight network in the world, it also made it economically very difficult to go away from our backwards compatible model. So first of all, you've got, with mixed freight and all the other variables, a lot of things have been done with the leader system and with train control in general to be able to accommodate for many of those things. We have a number of initiatives with a number of Class 1 railroads where there is a path to get to this level. And Rich, do you want to comment on that, or Bill?
I think you captured one of the challenges. I mean, the nice thing about ECP is it gives us another layer of information to add to that the safety case and understanding of what's actually going on at each of the cars in the train, and understanding the state of the brake system, as well as immediate understanding of any breakages that may happen. But additionally, there's a lot of peripheral systems that are provided as part of the overall auto haul system, in this case, but for an autonomous train operating environment. When you look at what we're doing is essentially taking the place of the decision-making portion of the brain on how, of a locomotive engineer's brain on how to effectively move the train from point A to point B, and trying to optimize that movement. The other part is how do we supplement his eyes, his ears, and make decisions on, if the tracks are being followed in front of us, how do we react to that or know that it actually happened. Those are some of the supplementary systems that have to be provided by some type of vision system, some type of other obstruction awareness, as well as making sure that the bell and the horn are working correctly. I mean, there's a lot of things that the engineer does today other than just move the handles to move the locomotive and get it from point A to point B. It's while it's moving from point A to point B, monitoring what else is going on and ensuring that that's done in a safe way.
The other thing I might add is that there's a human component to this as well. With the interest in autonomous trains, that has seemed to be taking some recent interest in North America. Some states have actually passed legislation to prevent the migration to single crews or no crews. So the unions see this as a threat to not only their membership, but to the human factor that's currently necessary to be part of safe train handling. So the regulations as well will have to change as technology changes. And this is where, and as I believe you have your an FRA representative within the room as well that may be able to add some color to this, but clearly whenever there's new technologies, regulations have to be part of that to make sure there's a controlled approach to introducing technology.
Other questions in the room?
I had two questions. The first goes directly to that, and the question is, what type of eyes and ears do you have on these locomotives, and what type of real-time monitoring is being done from a control center? Who's keeping an eye on these trains, and are they interacting with the operation of the train in any way? What's the role of your sort of central operator or dispatcher, if you have one? The other question is, has Rio Tinto made, or as a result of this technology, have they looked at making changes in train lengths? Has having access to this technology impacted the length of their trains, or suggested that there are maybe more optimal train lengths than the one they're using?
I'm going to punt that one to Rich. Rich?
Okay, I can answer the second question first. So the answer is yes, they're performing studies using the data that we were collecting over time, and they have made some adjustments to their train lengths currently. In some cases, shortening coming from certain mines, also lengthening coming from other mines. So there are continuous studies being done. They're also looking at wear and tear on different tracks. So based on the current way we've implemented the operation of the train, now that they've got some consistency, they've understood in certain areas that they don't want us operating with, say, only dynamic brake on the head end, that they may want us to distribute the braking a little bit greater in certain areas throughout the entire train. So depending on the different elements, they are looking at different efficiencies, both as well on the train length side and maintenance side, to understand what can be done to overall improve that now that they've got consistent data coming in. I didn't quite hear the very first question. I apologize.
Just a question about what type of monitoring, what type of real-time information are you feeding from the trains to a control center? Is there a role for an operator? You don't have an operator on the train, but you effectively have an operator at a control center who's making decisions about the operations of the train, and what information do they have available to them?
So in general, the real-time data that's fed is the basic data of speed, location, and so forth. That's the standard information that's being fed. Now, in the case of, say, an error condition that may occur on a particular train, there is the provision for a remote driver to get the train into an improved state or deal with a particular condition that has caused the train to go into an error state. One of the things I'm proud to say is that our system has not been part of the issue with any of these things to this point, but there's so many sensors on board the locomotive for the vision systems, for track following, all the various different understanding whether or not the lights are working properly and so forth on the train. There have been a number of issues they've been working through slowly but surely, and that cause a fault condition on the train, a fault condition I should say, on the train that causes them to have to operate either locally or remotely. They try to do it remotely as much as possible, but if necessary, they will fly an operator out to rescue the train, which right now has been very infrequent.
Just to back up a step, you have communication within the train consist, within the train system, and then you have between the train and the back office. So as Rich is saying, you've got a very tight integration of sensor data compared to what's built into the leader plan, and they're managing against those variances all the time. And as he said, if there's something with something throws an error, something comes in from the outside, they deal with it accordingly. And remember also, in this particular case, you really don't have grade crossings. You really don't have interchange. You really don't have a lot of the things that ruin our perfect world here in North American interchange, right? And we freely acknowledge that. There's improvements in technology coming for visual sensors and for other things. Bill pointed out the legislation and the real practical barriers to taking people out of the cabs. We're about improving throughput here. We're not about taking people's jobs necessarily. And there's a lot of enhancements that can be built into that train system. And there's, of course, further improvements with how we manage it from a back office. Yes, sir.
Yeah, I guess kind of following on the point you just made, and I was thinking this as you were giving the presentation. You know, in some ways, this is the ideal system, you know? And this is what I'm going to say next is not a criticism of New York Airbrake at all or anything else. But I noticed that there's still some perturbations of the system that occur. You referenced it during the presentation. It's kind of interesting to think about whether this represents kind of the ultimate that can be done, and then sort of home in on those last remaining sources of variance. And put another way, you know, this could be used as kind of a barometer or a metric to compare other operations to. So if this system is at 98%, other systems, whether they're in the United States or elsewhere, are at 70% or 80% or whatever it is, sort of understanding what the delta between what's possible and what's actually achieved in various different systems, again, is a way of homing in on where the greatest opportunities for improvements in whatever.
You make a fantastic point. And we are deployed with Leader with a manned locomotive on 2 Class 1 railroads all day, every day here in the United States. It was primarily, the first interest in it was energy management. We need to save fuel, so we need to balance the train. As they've embraced precision scheduled railroading, geez, we're not building these trains very well anymore. We're building them longer and faster. So the train balance algorithm became far, far more mission critical than it had ever been. This was a new variable. Nobody foresaw this 3 or 4 years ago. And Leader has been a tremendous tool for these guys on a manned locomotive, on an auto rack train, or some of the other more hairy ones to handle if they're in rolling or mountainous territory. You know, that said, what we have here in Australia is, boy, we plucked the low-hanging fruit here, you could argue as well. But until you do that, you can't get up the tree to get to the smaller stuff, and that's what we're trying to pursue now. Enhanced optical sensing, any number of things that either help a man-machine interface or make it an autonomous train.
Excuse me, any other questions in the room? I've got a few questions online. I can always stand here asking questions all day if I really wanted to. There's some questions online. You know, you have the video, you have the train rolling into the final loading station. What do you use for a parking brake or a hand brake, since you don't have a crew on the train? Do you have some sort of automatic parking brake, so to speak, for the train in those situations?
I can't speak for that particular train. Maybe Bill can.
No, I can. So the way it rolls into the station is we apply an independent brake, and it is met by an operator as soon as it rolls in. It is not allowed to just sit there by itself when it gets to a station. So that then the appropriate actions are taken, whether they're a parking brake on the locomotive, as well as setting any hand brakes on cars as necessary.
Next. Okay. Another question here, just related to what do you do with you know, if you do have to like set out a rail car or a bad order? You know, is that some of that 3% that's not being operated in autonomous mode? And you mentioned, you know, having to fly people out. I've been up to the Pilbara region there, and it's pretty remote in terms of getting access to people. And, you know, how does that impact the response time of getting to a disruption or incidents versus having someone on the train who's potentially facing a several-mile walk back along that train?
Well, once again, the wired ECP system eliminates a lot of those issues. And the way these trains are running back and forth, up and down, eliminates a lot of the variance as well. But Rich is the man who's actually been there who can answer it even more specifically.
Yeah, I mean, the majority, they're doing a lot of preventive maintenance to ensure that that is minimized. So it is an extremely remote case where they've had to do that, where they've had to bad order a car or have a train separation. It's extremely rare. They know the exact locations where those typically occur based on the terrain from a train separation standpoint. But bad order cars, they've got a number of measures that they put into effect prior to the auto haul program ever coming to fruition. So they've got a program in place to monitor the cars before they leave mines, before they leave the ports, so that they can understand if there's any issues with the cars. Again, as Chuck mentioned, We've got ECP that's part of the mix. So there's communication about the brake system itself that's continuously happening. And then again, as I mentioned, with the constant data that's being fed from the train, if we look at what we feed from a data perspective, and I say constant, I don't mean that it's every second. I mean that it's every. We download log files at the end of every single run that we make. Those are provided to various different departments as part of the database, and that is analyzed to understand if there's a degradation in operation of the train and or the various vehicles that are contained within the train, locomotives and cars alike. So they are spending a lot of time, and they've got a lot of manpower invested in ensuring that the vehicles themselves are in good condition before they ever embark on this trip.
I would only add that the model for this is much closer to what you would see here in civilian aviation than a big boy coal train rolling out of the Powder River Basin in terms of the maintenance level, the level of inspection, and the resources applied to it. Very different animal in that regard.
Just a couple more online questions. One is you talked about the need for the pusher or bank engines. Would this support distributed power locomotives, and is that just how they choose to implement their system based on the need for extra power?
I'm pretty certain it's their choice because it's just to push that train out of that mine and then the next one comes on. You don't need it for the rest of the run like you would in a more conventional DP scenario.
Okay. And final question, this is probably a tricky one, is what would it take, or what's the pathway to potentially get this certified and meet the requirements of a U.S. or North American implementation of a variety of different systems involved?
Not to be a smart aleck, but we have a lot of committees for that kind of thing. And frankly, there's a number of Class 1 railroads that are looking at this in big pieces, in strategic pieces today. And the idea being what can benefit us, what is legal, what is manageable, and what gets us a financial return. And this move to precision scheduled railroading, as I mentioned a minute ago, has really been a game changer in so many ways. I mean, many people stand on either side of the issue, but fundamentally it's what the manufacturing community saw with lean and agile many, many years ago. We are running assets to the absolute max and get the absolute greatest turn on them. And by doing that, it changes our focus on how we're working with equipment because you don't have a backup, you don't have redundancy. So a lot of this stuff that would seem like a science fiction fantasy or a luxury just a few years ago, it becomes a financially viable tool.
I guess one more comment I'll make is kind of a follow-up to Dr. Barkin's point about this being an ideal system for an ideal application, and you also, just because of the remoteness of the Pilbara region, you also have an ideal reduction in cost for eliminating the crews. When I was there, they were talking about someone who's stationed in Perth, which is already fairly remote by large cities, goes by. If you take them up to the Pilbara region, their cost of employment goes up 2.5 times.
Exactly.
So,
this is, and Rich can comment on this very specifically, this is a very different financial model than what we're accustomed to here. So the return on this technology is much greater, much faster than it might otherwise be.
Yeah, and ironically, you're 100% right, and that was actually only like when we look at the overall financial model, the cost of the actual crews themselves wasn't in the top 5 of financial returns to get this project going, which is was astonishing to me because I would have thought that would have been number 1, understanding the wages that we're talking about. But just the sheer time that they were saving on the crew changes and resulting getting the iron ore through on a regular basis, we're talking basically $40 million an hour here. So it's an impressive financial return that we're talking about.
Yes, sir.
I'll ask one more time, checking online.
And I apologize if you talked about this. I mean, I'm assuming you have train meets going on?
Yes.
So we can use the letters PTC, but there's some train control system that's managing all of that essentially perfectly?
I believe it's an Ansaldo system that's installed down there. And as an added one, maybe I'll head up a question or create more, I don't know. But we have also, where we are in revenue service with Leader today, we are PTC integrated.
If I can, Tyler will let me. So one of the things you very diplomatically handled was the matter of ECP brake implementation in North America, which, as we all understand, was, looking to be a very costly investment. And I think there was some concern that it was not really going to be cost justified. And ultimately, the FRA retracted its proposed mandate for ECP brakes. But as with anything in the railroad industry, if it's cost effective, the railroads will adopt it. So what I'm sort of thinking I'm hearing you're saying is that ECP brakes are a key to how well this system works. Is that an overstatement of what you guys were saying?
They made this a lot more linear, straight, direct. I don't want to say easier because there's so much work involved in this, but it was one less thing to have to factor in.
What I'm getting at is,
it's not required. It's not a required element, but it does add additional sensing and train makeup data to the overall operational standpoint from the single locomotive at the head end of the train. So while it's not required, it is a great way for us to be able to understand what's going on in the train, as well as improving how we can actually operate the train.
where I'm going with this, of course, is, it would be interesting to sort of look at the cost effectiveness of ECP brakes again if autonomous trains were part of the equation.
Without being too much of a provocateur and trying to be a diplomat, what I would say is recent rulings in Canada concerning oil trains, limiting them to 25 miles an hour, would be a wonderful way to look at this. And those who are that into this stuff may know that it was very recently that the FRA rules were retracted, that we're either going to put a severe speed limitation on oil trains or enforce the use of ECP. And that kind of went away about the beginning of the Trump administration, if I got it timed right.
It actually started before he was elected, but yeah.
That seemed to be the final straw. And I'm not here to be political. But what I would say is the rail industry today has accepted a 25-mile-an-hour oil train as financially superior or more beneficial than putting ECP on unit oil trains. I mean, that's where we're at right now today. To run those numbers again and challenge that math, I think it's probably something worthy for somebody to do. But it's certainly controversial as well.
I'm not sure I agree that the Canadian roads have accepted 25 miles per hour, but we don't have to have a big...
No, they got blockades to worry about.
0 miles an hour.
Yeah. One last question from online here, or unless we had any other in the room, students or anything. All right, one last online is, does the system help you potentially to enforce speed restrictions or traction limitations at places like bridges or other special track work where you're considered about longitudinal train forces that maybe a train crew is not going to think about, but you can program that into your system from a track health standpoint?
Absolutely. Now, the question becomes is how flexible are we with that and how real time are we with that? And that's where we continue to get better. As we continue to innovate with the system, it can do pretty much anything we tell it to do. So it's a question of how do we tell it, how do we enforce that, and how do we get the good link between the back office and the train crew. These are all enhancements that we continually are working on.
That's why autonomous trains are important for our infrastructure students here.
That's right.
All right. Anything else from the room before we close today? All right, well, thanks again to Rich and Bill.